This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion. We'll be delving into a research paper focusing on scaling large vision language models, VLMs, for enhanced multimodal comprehension in biomedical image analysis, specifically within the context of low-dose radiation therapy, LDRT. The authors address the limitations of off-the-shelf VLMs in handling domain-specific data and their propensity for hallucinations. Let's start with the core problem. Why are existing VLMs insufficient for this task?
Existing VLMs often struggle with domain-specific data because their pre-training datasets lack the specialized vocabulary, image characteristics, and contextual information prevalent in biomedical imaging. This leads to poor performance and a higher likelihood of hallucinations, the model fabricating information not present in the input data. In the critical field of medical image analysis, hallucinations are unacceptable as they can lead to misdiagnosis and flawed treatment plans.
The paper mentions the use of LLAL models. Can you elaborate on the choice of this architecture and its suitability for this application?
LLL, open source nature, and well-documented architecture make it an excellent foundation for research, reproducibility, and adaptation. Its three main components, a pre-trained language model, a vision encoder, and a cross-modal projector allow for effective integration of visual and textual data. The modular design facilitates fine-tuning for specific tasks, which is crucial for addressing the limitations of general-purpose VLMs in the biomedical domain.
The paper describes a two-phase training process, projector alignment and instruction fine-tuning. Explain the purpose and mechanics of each phase.
Projector alignment focuses on optimizing the cross-modal projector, which maps visual features from the vision encoder into the language model's embedding space. This ensures that the visual and textual representations are compatible and can be effectively combined. Instruction fine-tuning then fine-tunes both the projector and the language model parameters on a domain-specific dataset, enabling the model to perform the desired downstream task, in this case, visual question answering on LDRT images.
The data preprocessing pipeline seems quite involved. What were the key steps and challenges encountered?
The process began with gathering a large corpus of LDRT-related articles using keyword searches and Semantic Scholars API. This yielded a substantial number of articles, but the conversion to a usable format, Markdown, and extraction of images and captions presented significant challenges. Filtering out low-resolution and bluey images was also crucial to ensure data quality. Finally, generating high-quality question-answer pairs using an LLM, Quinn272B instruct, required careful prompt engineering and filtering to ensure relevance and accuracy.
The paper highlights the use of several optimization techniques during fine-tuning. Why were these necessary and what were their specific contributions?
Fine-tuning large VLMs is computationally expensive. Memory optimization techniques like gradient checkpointing and flash attention to were essential to manage the memory footprint and enable training on the large dataset. DeepSpeed 003 facilitated efficient model and data parallelism, significantly accelerating the training process. Finally, low-rank adaptation, LoRa, reduced the number of trainable parameters, further improving efficiency without sacrificing performance.
The evaluation methodology employed in LLM as a judge approach. Discuss the rationale behind this choice and the metrics used.
Using LLMs like Quinn272B instruct and Llama 3.170B instruct as judges provides a more objective and nuanced evaluation than relying solely on automated metrics. These judges assess the model's responses based on relevance, helpfulness, and accuracy, providing a holistic assessment of performance. The consistency in scoring between the two judges validated the reliability of this approach. Additionally, Rouge scores and analysis of linguistic markers of uncertainty, like hedging language, provided further insights into the model's factual consistency and confidence.
The results show improved performance compared to the base ALL models. Can you quantify these improvements and discuss any trade-offs observed?
The fine-tuned models consistently outperformed the based ALL models across both detailed description and complex reasoning tasks, as judged by the LLMs. However, there was a trade-off observed with LLALL v1.6 Vicuna 13b, which showed better performance on detail-type tasks but exhibited increased verbosity. This suggests a potential balance between verbosity and reasoning depth that warrants further investigation.
What are the key limitations of this work and what avenues for future research do you see?
The current study focuses on LDRT. Expanding the data curation and model training to encompass other biomedical applications is a crucial next step. Further refinement of the hallucination analysis pipeline is also needed to better understand and mitigate this issue. Exploring different model architectures and training strategies could also lead to further performance improvements. Finally, rigorous clinical validation is essential before deploying these models in real-world medical settings.
The paper mentions a significant reduction in hedging language in the fine-tuned models. How does this relate to improved factual consistency?
Hedging language, DG, appears, likely, possibly, often indicates uncertainty in the model's predictions. The significant reduction in hedging observed in the fine-tuned models suggests increased confidence in their responses. This increased confidence, coupled with improved Rouge scores, indicating better alignment with ground truth, strongly supports the conclusion that the fine-tuning process enhanced factual consistency.
The computational resources required for this research are substantial. How did the authors manage the computational challenges?
The authors employed a combination of strategies to address the computational demands. They used a compute node with multiple high-end GPUs, optimized memory usage through gradient checkpointing and flash attention 2, and leveraged deep-speed ZR03 for efficient model and data parallelism. Low-rank adaptation, LoRa, further reduced the number of trainable parameters, making the training process feasible within their resource constraints.
The paper emphasizes the importance of factual accuracy in biomedical applications. How does this work contribute to improving the reliability of VLMs in this domain?
This research directly addresses the issue of hallucinations in VLMs, a critical concern in biomedical image analysis. By fine-tuning the models on a large, carefully curated dataset and employing various optimization techniques, the authors significantly reduced the incidence of hallucinations and improved the factual accuracy of the model's responses. This contributes to building more reliable and trustworthy VLMs for use in medical applications.
The use of a Laplacian variance method for image filtering is interesting. Can you elaborate on its role in data preprocessing?
The Laplacian variance method helps identify low-resolution and blurry images by measuring the variation in pixel intensities. Images with low variance are considered blurry or low resolution and are filtered out. This step is crucial for maintaining data quality and preventing the model from learning from noisy or unreliable images, which could negatively impact performance and increase the risk of hallucinations.
The paper mentions the use of 20 template questions for generating detailed descriptions. What was the rationale behind this approach, and how did it contribute to the quality of the training data?
Using template questions ensured consistency and coverage in the types of detailed descriptions generated. This approach helped create a more balanced and comprehensive training dataset, improving the model's ability to generate detailed and accurate descriptions of biomedical images. The use of term frequency, inverse document frequency, TF-IDF, vectorization, and cosine similarity further ensured that the LOM-generated answers were relevant to the corresponding template questions.
The choice of a cosine decay learning rate schedule is common in deep learning. What are the advantages of this approach in this context?
Cosine decay is a learning rate schedule that gradually decreases the learning rate over time following a cosine function. This approach helps to stabilize training, prevent oscillations, and potentially improve the model's ability to converge to a good solution. It's particularly useful in fine-tuning large models where a more gradual reduction in the learning rate can be beneficial.
The paper mentions the use of LoRa for parameter-efficient fine-tuning. Explain how LoRa works and its advantages over full fine-tuning.
LoRa, low-rank adaptation, is a technique that adds low-rank matrices to the pre-trained weights of the model instead of fine-tuning all the parameters. This significantly reduces the number of trainable parameters, making the fine-tuning process much more efficient and requiring less computational resources. It often achieves comparable performance to full fine-tuning while being significantly faster and less memory-intensive.
The use of both detailed description and complex reasoning tasks in the evaluation is noteworthy. Why is it important to evaluate the model on both types of tasks?
Evaluating the model on both detailed description and complex reasoning tasks provides a more comprehensive assessment of its capabilities. Detailed description tasks assess the model's ability to accurately describe the contents of an image, while complex reasoning tasks evaluate its ability to understand and reason about the relationships between different elements within the image and its context. Both types of tasks are crucial for a robust and useful VLM in biomedical applications.
The paper mentions the use of a batch size of 16 across 4 GPS. What factors influence the choice of batch size in this context?
The choice of batch size is a trade-off between memory usage and training speed. A larger batch size can lead to faster training but requires more memory. The authors chose a batch size of 16, distributed across 4 GPUs, to balance these factors and ensure efficient training within their available resources. This batch size allows for parallel processing while keeping memory usage within acceptable limits.
The authors used a temperature of 0.2 during inference. How does the temperature parameter affect the model's output?
The temperature parameter controls the randomness of the model's output. A lower temperature, like 0.2, makes the model's predictions more deterministic and less creative, leading to more focused and less diverse responses. This is often preferred in applications where accuracy and factual consistency are paramount, such as in biomedical image analysis.
The paper concludes with a discussion of future work. What are the most promising directions for extending this research?
Expanding the data set to include a wider range of biomedical applications and modalities is a key priority. Further research into improving the robustness and reliability of VLMs in handling noisy or incomplete data is also crucial. Finally, developing methods for better explainability and interpretability of VLM predictions is essential for building trust and facilitating wider adoption in clinical settings.
This has been a very informative discussion on the advancements in scaling large vision language models for biomedical image analysis. Thank you.